Okay, welcome and thank you for joining us for our Working Towards a Zero Waste World virtual workshop series that's kicking off today. Today's focus is on sustainability in plastics production and recycling. Today's event is co-hosted by Boston University's Institute for Global Sustainability, the Energy and Sustainable Technologies Lab, and the College of Engineering. My name is Eric Cuny. I will be one of the facilitators for this webinar. I'm an assistant professor in the chemistry department and affiliated faculty member with the Institute of Global Sustainability here at BU. The recording for today's webinar will be available on IGS's website at bu.edu/IGS and emailed to everyone who registered. To ask questions during the webinar, please use the Q&A button at any point, and we'll get to as many of the questions as we can during our Q&A period after all of the speakers have presented. Now we'll introduce our speakers as well as my BU colleague that's joining me to facilitate this webinar. So from BU, we have Professor Malika Jeffries-L will be the other facilitator today. She is a professor of chemistry here at BU, as well as a core faculty member with the Institute for Global Sustainability. And now for our speakers. So today we will hear from, in this order, Alex Balzer, who's a postdoctoral researcher at the University of Delaware. Alex is currently working as part of the Center for Plastics Innovation that is based out of the University of Delaware. Next, we will have Luis Falcon, who is a recycling I&T platform leader at Braskem Chemical. Luis brings more than 30 years of experience in the petrochemical industry in a wide variety of roles, including R&D, business development, and portfolio management. And last, we'll hear from Aaron Sadow, who is a professor of chemistry at Iowa State University and a senior scientist at Ames National Laboratory. Aaron is also the director for the Institute for Cooperative Upcycling of Plastics, ICOUP. So with that, thank you all for joining us, and we'll let Alex take it away.
I can share everything for you guys. All right, hopefully you see the proper view and you hear me all right. Thumbs up means we're good to go. Thank you so much for the introduction and thanks for having me. I'm excited to talk about our work at the University of Delaware and the Center for Plastics Innovation, particularly on tracking polymer chain transformations as they undergo different polyethylene deconstruction processes. I'm mostly going to be focusing on some of our work in polyethylene hydrocracking, but I'm happy to discuss a lot of other avenues we explore. So we're all here to talk about plastics sustainability and tackling the plastics waste mismanagement worldwide, where over 90% of plastics are either landfilled or incinerated, kind of fall into this category of mismanaged for the most part. And only 10% of plastics, or just under 10% of plastics, are actually recycled. And so we're trying to target different ways to improve recyclability, whether that come in the form of new plastics that have some sort of intrinsic circularity, easier to recycle chemical bonds, but also kind of rethinking materials composition, targeting bio-based and biosustainable feedstocks instead of traditionally petroleum-based feedstocks, designing new chemical recycling pathways, whether it's through some catalytic or chemical deconstruction, like I'm going to talk about today, but also we at CPI focus on biological deconstruction methods of polyethylenes. And we also try to target chemically upcycled plastics and polymers, turning these low-value plastics that we get from waste into some high-value, high-performance materials. But like I mentioned, today I'm going to talk about our chemical deconstruction pathways, particularly of polyethylenes and polyolefins into high-value products like liquid hydrocarbons that can be used in fuels, waxes, and lubricants. And so the way we go about this is through the catalytic hydroconversion of the polymers, which is basically we can take our pristine polymer feedstock, feed it into a high-pressure reactor along with some sort of catalyst and hydrogen, hence the hydroconversion part of this process. And after a certain amount of time, we can separate the products from this reaction into three components: the gases, liquids, and solids. And so traditionally at CPI, as well as in the community, there's been a lot of focus on how you can design catalysts to get certain selectivities and yields out of your gas and liquid products, but there isn't as much focus on the solids. But at CPI, we've developed a lot of different catalysts, ruthenium-based, platinum-based catalysts, as well as some cheaper nickel-based catalysts that can kind of help, as I mentioned, target certain feedstock or certain products like fuels or lubricants, and that comes down to certain catalyst designs. But we also should really focus on what sort of polymer you're feeding this feedstock and how that affects all these transformations as well. And because polymers and plastics are extremely complex, and you can, as a polymer scientists, we really wanted to focus on all the different forms and all the different chemical structures that the plastic can exist as. And for one, if we were to just look at the general forms that you can find these polymers in, because they're found in these plastics wastes, they can be in the form of pellets or powders or films. They can be a part of multi-layered materials that have several different type of plastics found inside of them, generally used for a lot of like single-use plastics for oxygen barriers or water barriers. But you can also kind of zoom down on the length scale a little further to look at the different sort of additives that are found in plastics or contaminants, as well as all the different macromolecular features of these plastics. Are they cross-linked? Are they heavily crystalline? Are they mostly amorphous? All this is going to play a role into one, where the plastics is used and what sort of waste we're going to see from it. But it also should affect our catalytic deconstruction of these processes as well. And so what we also like to tackle is that plastics themselves are not just the polymer. They're very complex. They have a lot of different additives that can come in the form of fillers and flame retardants, antioxidants. All of these things help impart some sort of mechanical thermal stability that makes it easier for them to process, easier for them to stick to different layers for these multi-layer plastics as well. And if we were to just kind of take an LDPE food bag for an example, you're going to find everything from a bit of antioxidants, which helps the mechanical thermal stability during processing, to fillers like calcium carbonates or silicon dioxides that help with color, to help them look more white, but also reduce their overall cost. You can also have different copolymers added into these bags to help some sort of feel, texture, or even toughness of the material. And then you're also going to see things like pigments and fillers that, if you have some sort of logos on these bags, or if you want it to have a particular color, these are also common plastics. So polyolefin-based plastics themselves are really complex in just their composition. And then zooming down one more time, we can kind of look at the general chemical structure of these polyolefins, which polyolefins make up a little over half of the total number of plastics produced. But polyolefins themselves can be generally separated into polyethylenes and polypropylenes. And then when we talk about polyethylene itself also has three major form factors: high density, low density, and linear low density polyethylene. And so it's important to kind of keep all of these different chemical structure complexities in mind as you start to design catalytic deconstruction methods. Now you're going to track how this polymer changes throughout your whole reaction. So if we go back to the hydrocracking of the plastics, we took linear or a low density polyethylene, LDPE, fed it into our hydrocracking reactor with a particular catalyst. And what we wanted to do was first see if we could understand all the different transformations that chain can go through during the reaction. And so what we know from our catalyst is that the polymer chains can either not react with the catalyst, hence have unreacted LDPE in there. They can isomerize over our catalyst, and they can also deconstruct, so they can break down molecularly. And all three of these components make up that solids distribution. They're all just intermixed, and it's really difficult, nearly impossible, to actually separate all of these different chains from each other. So we needed a way to track all these transformations and how that affects the general process and interactions with the catalyst. So what we did is we first kind of looked at the unreacted and isomerized LDPE. What we notice from these two is that they're the same molecular weight, even though they have slightly different architecture. This poises them really well for gel permeation chromatography, high temperature GPC, where we can look at the molecular weight distribution of these materials, shown here on the right side, where the black curve is our neat LDPE, and the red solids curve is what we're getting out of that reactor. And what you can see is the solids curve is it's a wider distribution, kind of has this bimodal-like feature. But on this high molecular weight tail of this solids curve, looks nearly identical to the high molecular weight tail of our neat LDPE feedstock. And so we can actually take our LDPE feedstock distribution and fit that inside of the solids curve to help us define this intact LDPE fraction. And that is going to contain all of the unreacted and isomerized chains. From that, we can actually subtract the intact LDPE from the solids curve, and that helps us understand the new deconstructed chains that exist in this fraction. So these are new polymer chains that exist in the product distribution. So what we did is we tracked both the intact and the deconstructed LDPEs over the course of the reaction. And what we see is that early on in the reaction, so after 1 hour, we get a large amount of deconstructed LDPE at very low molecular weights. But then as the reaction progresses, this distribution starts to widen and you get a lot more to intermediate level molecular weights. And so what that tells us is that there is this changing mass transfer and diffusion aspect during the reaction. And we can kind of think of it in terms of how fast polymers actually diffuse and how fast their diffusion viscosity is compared to general materials you may see in everyday life. And ultimately, polymer chains diffuse on timescales that are tens of thousands of times slower than most small molecules. And so what we're seeing during these reactions is that actually a chain diffuses to the catalyst surface and it has to undergo several chain scission processes until it's a small enough molecule that its diffusion timescale is actually fast enough to move away from the catalyst before another chain can come in and interact with this catalyst. And that's what gives us this really low molecular weight distribution early on in the product or in the reaction time. And then as the reaction time increases, slowly the viscosity of your overall reactor decreases. And so you're going to get more and more chains with higher and higher diffusion during this. And that gets that sort of broadening of the molecular weight distribution. But we also wanted to look at the other parts of these solids, which is the isomerized and deconstructed LDPE, which can be kind of characterized as their reacted LDPE, because regardless of what transformation it went through, these two products had to interact with the catalyst. And the way we can kind of understand this is through the crystalline structure of our solids after the deconstruction. If we look at how a polyethylene crystallizes, you get one chain that starts to line up with several more, and really the length that the backbone crystallizes in is called the lamellar thickness, which is generally related to the melting temperature of the crystal. And if we wanted to see how large of a crystal we can make, in the case of low density polyethylenes, the largest crystal you can make is actually limited by how far apart your branches are. That's because once you introduce a branch into this polymer chain, it effectively acts as a defect in your polymer or in your crystal. And that limits how large of a crystal you can actually make. And so we can actually convert melting temperatures of these crystals into methylene sequence lengths, which is basically how far apart the branches are. If we were to look at that using differential scanning calorimetry, we get this really unique distribution of melting peaks through a self-seeding and annealing procedure, where we can actually take all these different melting peaks, fit them to a number of Gaussians, and then calculate the area and the peak temperatures of all these, which basically gives us the branching architecture graph I'm showing here on the right, where your y-axis is how much of a particular crystal length exists, and your x-axis is how large that crystal is. And you see in LDPE, we get this steadily increasing branching architecture, but then the solids distribution looks nearly identical until the longest methylene sequence length at about 100 carbons, which we then, similar to the TPC, recognize that if your LDPE interacts with a catalyst, it has to change its methylene sequence length, the distance between branch bonds, whether you isomerize it or cut a carbon-carbon bond. That distance has to change. So anything that exists that is 100 carbons long in the solids distribution would be unreacted LDPE. And so we can fit that distribution just like we did the GPC. And then the residual of the solids distribution would be our reacted LDPE fractions. And just like the GPC, we can look at the change over time of these methylene sequence lengths. And what we see is that over the course of reaction time, the longest methylene sequence length starts to decrease first, followed by the second longest length, followed by the third longest length. And so basically, what that's telling us is that when we look at the LDPE chain, the most linear portions, so the furthest spacing in between branches, act as the strongest absorbers to the catalyst. They preferentially interact with this catalyst, while the areas that have a lot of branches nearby are very sterically hindered. They don't want to interact, absorb to the catalyst as much. And so that's how we can start to understand how the polymer architecture, where the branches exist, how many of them exist, affects your catalyst activity and kinetics. But from this, we basically were able to identify our intact yield, our reacted yield. So we basically have two equations, or we have three equations with three unknowns. We solve a mass balance to basically back out the number of, or the fractions of unreacted, isomerized, and deconstructed chains throughout this hydrocracking. And I'll just point out that even at the longest reaction times of 4 hours, we still have unreacted chains inside of these solid yields. So that means that there are still chains that haven't even interacted with the catalyst, even though you can still see on a mass balance an 80% drop in mass of your solids. And so this really comes back to understanding the kinetics and the diffusion of these polymers and how that really affects your reaction progress. So now we kind of have this way to track the very, very small architectural changes. So we can like keep zooming out and understanding more and more about the plastics during their hydrocracking. So like I said, since we have a way to track the changes, we're starting to investigate how the different branching architectures affect your product yields, how their molecular weight distributions affect your yields, because now we've kind of unlocked this pathway to understand it better. But we also can zoom out towards the composition of the plastics that I was talking about. How does all these additives that are in these plastics affect the deconstruction? And so we looked at a few different antioxidants during this hydrocracking process. And what we noticed is that in the presence of no antioxidants, this strict high density polyethylene, in this case, not low density, gives the greatest liquid yield on a mole basis, a carbon mole basis, which is really the high value targeted product in our hydrocracking process, which is what we want. But when we start adding antioxidants, depending on their chemical structure, it poisons the catalyst surface, deactivates the catalyst. And so we can start to understand, what sort of antioxidants, what sort of fillers or plastic additives you may have in your feed that affects your process. And just in the case of something like this Ergonox 3114 has these nitrogen rings inside of them that deactivate the catalyst almost immediately. And so we get nearly no liquid yields and we get no reaction progress in this system. But we can also zoom out again, like I mentioned, into this form factor and understanding what size of your plastic is going to affect this process. And so we actually looked at a series of pellets that we fed in a reactor, which are on like the millimeter to centimeters scale, and compare that to a powder of the same polymer that we formed that has more of a micron level scale. And what we see is that the powder HDPE has a higher liquid yield for the same reaction time compared to the pellets. And that's because really in the pre-mixing step, we can get more catalyst to polymer interactions because of just the size distribution. And in the case of the strips, what we see is an even higher yield. But what I also want to point out is that the distribution of our liquid yields actually doesn't change significantly with the form factor. It's just you get a faster reaction. And so this is really back to like the mass diffusion limited process. If you have really large plastics in shape and size, they're gonna just react slower. It takes them longer to diffuse and reach the catalyst surface compared to like something that can be ground up extremely small. And we also saw similar trends in the solids that came out of this, in that in the same fashion that we saw higher liquid yields of something like a powdered HDPE, the intact HDPE that also existed in these solids was lower than that of the pellets. So kind of confirming the same sort of diffusion limited mass transfer problem. So hopefully I kind of pointed out a lot of different complexities of plastics waste and how they affect a lot of different deconstruction pathways. And so we've developed a method to track all the polymer chain transformations. So that'll help us understand a lot about the architecture and how it affects interactions with the catalyst, how it may affect diffusion, mass transfer, phase separations as well, because a lot of branched polyethylenes can phase separate from linear polyethylenes. But also understanding the plastic as a whole and how its composition, its form factor, presence of additives, contaminants, antioxidants also affects your deconstruction. It can take, and certain antioxidants can poison catalyst sites, lead to decreased activity. But we really hope that really understanding the plastic as a whole, everything from its molecular architecture all the way up to its compositional and shape factor, will kind of lead to better process and economic analysis, process design and economic analysis, to further advance both, hydrocracking of polyolefins, but the catalytic and chemical deconstruction of multiple different types of plastics, to higher value products, and kind of lead to this more circular based economy. With that, I'd just like to thank both of my advisors in the groups, Dr. Corley and Dr. Epps at the University of Delaware, and previous postdoc, Dr. Zach Hinton, who I worked on with these projects, and the Center for Plastics Innovation for funding all of this research as well. So I guess I'll leave it here, and we'll have questions later on.
Excellent. Thank you, Alex. Yeah, like Alex said, we'll have Q&A at the end. So if anybody does have questions for Alex or any of our other speakers at any time, you can put it in the Q&A portion. Okay, so next up we'll have Louise.
I think you can hear me, right?
We can hear you, yes.
Okay. I don't think I can start my video. I think the host has to do it.
Okay.
Okay.
Oh, there it is.
Okay.
Excellent.
There it is. So I'm going to share my screen.
Excellent.
I hope you can see the right screen.
Oh, can you actually flip it again?
Okay.
Excellent.
Now you have it. Okay. So I'm going to take you now to the view of the industry, right? So I kind of merged some different presentations to get to something that I believe will be interesting for everyone. So initially, I will go faster on this because I believe everyone has this view, right? On the scene we have, the problem we have related to plastic waste, and also the importance of having plastic on our lives, and on different applications that has impact on sustainability and other applications. So this is something I believe I can go faster as well. And as well was mentioned, of course, depending on the source, you have different figures, but the same point made before is that most of these plastic really becomes waste in a small volume, 10%, 15% is already recycled, and the other part will be incinerated, landfilled, or different destinations, including leakage to the environment. And it depends on different countries has different configurations for that. So I brought the example of Europe. So you can see different countries in Europe have different configurations on recycling. You see that there is a lot of energy recovery as well. Some countries almost don't landfill anymore. Others still have a lot of landfilling. So this also gives an idea that that's a movement ongoing, right? And we have different levels of engagement and different levels of solutions in different countries. So the concept that the industry believes it's the path is to migrate from a linear economy to a circular economy. So the traditional linear economy for plastic, going from the source all the way to the consumer, should go back, and through waste management and roots on mechanical and chemical recycling. And on that direction, my company, Brasking, has these commitments to have 1 million tons of circular product by 2030. And at the same time, we have to achieve carbon neutrality on 2050. So these things are also related. And as I go through the presentation, I believe it will become clear what's the relationship between these two targets on plastic waste and climate change. And other industries have similar commitments and similar targets. So when we speak about innovation and technology or research and development, what is our target, right? On mechanical recycling, we're usually talking about very mature technologies, but there is still room for improvement, because usually this PCR generated on mechanical recycling has quality issues. So solving these quality issues is important to have new applications. And on chemical recycling, on short term, our idea is to use the commercial technology existing to develop recycled resins, and in long term, develop new technologies that will improve and go beyond the numbers we have today. So I brought some examples of initiatives on both of these fields. On mechanical recycling, as I said, it's a quite much mature technology. So we have an example of one company, the Braskem bought in Brazil, and to produce mechanical recycled products. And from this kind of initiative, we already have 58 products in our portfolio made of what we call We-New portfolio, from recycled resins and also bio-based resins. So on PVC, on PP, on PE, on rigid and flexible. So we have different applications. And going back to the point of the carbon footprint, we have some numbers showing that the circular or mechanical recycled resins, they have a lower carbon footprint than the virgin or fossil PE and PP. This is using Brazil production as a reference. And you can see the numbers from different kinds of applications, on circular applications. And we also have the carbon capture on the middle here. When we talk about the I'm green PE, is the sugarcane based PE that we produce from dehydration of ethanol. So this one has the capacity to capture, actually, because we are producing from carbon that's coming from plant-based production. But this would be a complete different presentation. I just brought this together on this LCA analysis. When we go to chemical recycling, we have several technologies that are being developed and tested, from the mechanical recycling to going to advanced or chemical recycling. We have dissolution, biochemical processes, the thermal process that is the more developed today in the commercial basis, and gasification and applications that we will incinerate and convert the CO2 from this incineration. So several different technologies and several others that are not in this chart that I found online. But we are already applying the pyrolysis technology. It's a thermal technology that you break the polymers and you produce a liquid phase that is a oil that goes through the production chain again. So the final product has the same quality and chemical composition of the original or virgin polymer. So you don't have the issues that you have on mechanical recycling. And you also can go through this process several times and infinite times that you need. So this is a big advantage on chemical recycling and the existing technology today on commercial applications, that is pyrolysis. This technology has its limitations, of course, related to carbon footprint, for example, to the presence of contaminants, to yields that you can achieve. So that's why, although we have already one solution, we are still searching for improved alternative and better technologies. And of course, since you are producing an oil that will go through the process, the chain of the plastic again, you cannot segregate this production. So how do you sell circular products? So we have to use this concept that is called mass balance, where you mix the fossil feedstock with the circular or bio-based feedstock, and you have a certification that makes sure that in the final product you have a content of these circular materials, and you can through this certification assign a certain quantity that based on the amount of feedstock you have used. So that's another limitation on this kind of technology, is that you don't have segregation, but you have this method to assure that you have circular product. So another example on this time on chemical recycling is an application we are doing in Europe, where Braskem is buying the pyrolysis product from this WPU plant in Denmark. Then this oil is sent to the Netherlands to an upgrader from Shell, and Shell sell us the circular propylene through this chain of custody, and Braskem can produce this circular PP in Germany. So that's one of the examples we have on this kind of applications. We have others in the US, in Brazil as well. And in terms of the development of technologies, how we believe we can achieve new and improved technologies through open innovation. And we have several partnerships with institutes and universities. Also development with partners. Here also one example, a partnership we have with TNO, this institute in the Netherlands, to develop solvent-based technologies. We have, of course, the offtake contracts and partnership to process bio-oil. I mentioned WPU. Here are two other companies, Vitol, Nexus Circular in the US. And we have also proprietary technology development on our labs. Specifically for this kind of technology, we have a lab in Pittsburgh where we work on that as well. So again, an example is on the very similar line that was previously showed here. We believe also in catalytic depolymerization. So we have a study and a development going on. The advantage is to get directly from plastic to chemicals with a lower carbon footprint, an opportunity for tuning the yields and being robust for contaminants. And here you have a picture of a lab scale unit that we are using for this one of these developments. And we also have what we call internally the Blue Sky program, where we explore alternative technologies, seeking options and seeking partners. For example, in fields like electrochemistry, plasma, microwave, enzymes. So very different technologies that eventually could be applied for that. And also we have these related companies to Braskem. Oxygia, it's an investment company that from that what we are looking for startups and new technologies to develop related to new materials. And also we have already one spin-off that is Sustenea, that we are going to produce biomag from sugar to be used on the production of PET. And also upside that it's upcycling of plastic waste to applications like pallets, road plates, and others. So these are some of kind of spin-offs or affiliate companies that Braskem created to help on this ecosystem and this development. And in the end here, I want to speak a little bit. As I said, this is a completely different, would be a different complete presentation. But as I mentioned, we have the green PE that has all these advantages. And we are on these bio-based materials. We are starting a new lab very close in the Boston region in Lexington. And the idea is to have all this know-how related to process technology, catalysis, biotechnology, and open innovation on this site. With very everything is new. It's a complete new lab, very well equipped to develop these bio-based chemicals. And some pictures, I'm just sharing some pictures of this new lab. So we'll certainly be needing talent and new researchers. And here's already a picture of some of these researchers that are already working with us in this Lexington facility. And so thank you for Eric and Boston University for inviting me and the opportunity to share this with you. And here are my contacts, and also I'm available for questions.
Thank you, Luis. It's very interesting to have your perspective. We'll continue to save questions for the end, but next we'll go to Aaron. And just as a reminder to everybody, you can type your questions in the Q&A portion, and we will try to get to them at the end.
Okay, does this look all right?
Yeah, looks
We're on the
great.
right side. All right, good.
Yep.
Okay, so I unfortunately missed a little bit of the intro. We had an exam that I couldn't miss. So hopefully I don't say stuff that's too redundant from what was already discussed. But I'd like to talk about one of the main thrusts that goes on in our Center for Plastic Upcycling that's funded by DOE-BS, part of an EFRC, I think, like Alex, the one Alex talked about. So let's see. Okay, to get to go. Let's make sure that's gone. So I hope we talked already about the implications of plastic waste on energy, on the environment, and the economy. These are, I think, as Luis said, really highly coupled. There's the plastic waste problem, but there's the fact that we make a ton, really a lot of plastic now. And we make a lot of plastic because it's really valuable, and we use it in all walks of life. The downside is, of course, what we're talking about, the waste and the fact that a lot of it's used once and then discarded. So this kind of single-use application, that's a lot where the value comes in. So the idea of saying that we would just bail on the use of these materials probably doesn't make sense overall in a sustainability perspective. But when we throw this stuff out, we're wasting really a lot of energy. And you can make some estimates, and ours looks like 1.3. We're throwing out 1.3 billion barrels of oil each year across the world from our polyethylene waste. So this is obviously not very sustainable. Okay, so within our center, we've been trying to develop catalytic technologies and understanding of ways to convert plastic waste into new chemicals to make recyclable polyolefins. And a few of those are highlighted here. There's really a lot of groups working in this area right now, and there have been a lot of nice advances. So I won't dwell on this too much. I think Luis pointed out kind of a little bit about some of the problems. So there are methods now that are in existence of mechanical recycling and pyrolysis that sort of set the boundary conditions for whether something might be adopted. So you can think kind of about the value of just milk jugs, for example, that would be recycled, and those are about $800 a ton in terms of waste. So if whatever you do, better make more money than that, at least if you're recycling milk jugs. However, there's another side of the problem. There's a lot of plastic that can't be recycled. So this is a picture of a bale from a company north of Ames, Iowa, that makes plastic packaging. And you can see how this is relatively clean waste, but you can see how there's really a lot of stuff that's different within the bale in terms of colors, in terms of additives. And in fact, there's lots of different polymers that go in, and that makes all of these kinds of waste and a lot of our MSW based plastic waste not recyclable and with conventional technologies. So that's an opening for basic studies on how to do these kinds of conversions. So the way we think about this in ICOOP, in our EFRC, is that the challenge could be broken down into kind of two parts. So one is that we want to break CC bonds in polyolefins and introduce functional groups. And that is going to add value to the resulting products. There's actually a pretty reasonable challenge there. If you think about the chemistry that's known in general, breaking a carbon-carbon bond and adding functionality is not actually a very common reaction in synthetic chemistry, and particularly catalytic chemistry. So that's one part of the challenge. But that's not necessarily only specific to polymers. And what I'd like to talk about today is really what the conversions or the features of these conversions, catalytic conversions that are specific to polymers. So we kind of highlight that here, the center point of this problem. So polymers or plastics are composed of long chains, particularly polyolefins, long chains, short chains, medium chains. There's a big distribution in that milk jug. You need long chains to get strength. You need short chains to have good processability to make the materials you want in the shapes that they want. That's not what we normally do in a synthetic conversion. You start with one starting material that's pure and you convert it to another product that at the end you hope it's pure. And so that's a challenge. And then the other challenge is that every bond in the plastic looks the same. There's no way to distinguish, say, hopefully we see the cursor, the 10th bond from the 20th bond. To a molecular catalyst, they're going to all look the same. So when you start breaking bonds, even catalytically, it's going to occur randomly, and you're not going to be able to get out one product. You're going to get a broad distribution of products. That's what happens when we pyrolyze. That's what happens when we use a catalyst that is unselective for a particular chain length. So in iCoop, we were trying to understand how we would break that sort of paradigm of random cleavage to be able to design catalysts to give chain lengths that might have specific value, or at least narrow how that happens. So it's somewhat instructive to think about how polymers are made in general, to think about how we might break them down. So there are kind of two general mechanisms. There's step growth polymerization, which would be random encounters of reactive groups at the ends of chains that start coming together. So monomers go to dimers, dimers go to trimers, dimers, mixtures, and these mixtures keep growing in length until at the end of the reaction at very high conversion, where you have very few reactive groups left, that's when you have the polymer. So that's a step growth polymerization. Polyolefins are made by an entirely different mechanism in general. That's the chain addition or chain growth polymerization, where you have a site or a few sites that are active and monomers keep adding to that site. So in the course of those polymerizations, you have monomers and you have long chains and very few species in between. So that's how polyolefins are made. We have, say, the Ziegler catalysts that you have active sites and you keep adding ethylene. And so the active chains grow, the inactive chains don't grow, and then you have a lot of ethylene around. So if we break chains randomly, if we took this polymer and you start breaking chains randomly, then that's the opposite of a step growth polymerization. And the mixture that you get out in this conversion, so until you get to a monomer, it's going to be a mixture of short chains, medium chains, long chains that are just governed by the statistics of random cleavage. And the control you can get is at the end of the reaction, if you're making monomers, you could make 100% monomers. So that's great. That works really well for things like PET, where you have monomers of specific size and specific units that could be cleaved, functionality that could be cleaved to build monomers that could be repolymerized. But from something like polyethylene, where the distinct monomer is ethylene, and that depolymerization is uphill by a large amount, you can't add a reagent to generate ethylene from polyethylene readily, then you have competing reactions, and it's very hard to get back in high yield to these monomers. So we were thinking, and I should say here I would give heavy credit to Baron Peters at UIUC now, who said, well, as we were talking about how to do this, well, how does nature do depolymerization reactions? And so he and Fred Perra in the Ames lab pointed out that there are lots of enzymes that depolymerize biopolymers, and they do it through what's known as a processive mechanism, where the enzyme catalyst will absorb a polymer chain and start eating it up, and the substrate polymer or biopolymer isn't released until all the small molecules have been cleaved off, all the monomers or whatever the units are that the the enzyme cleaves. So the question was, could we design an inorganic catalyst that would work in the same kind of way with something like polyethylene or polypropylene to allow us to build selectivity into the deconstruction of these non-step growth polymers? So the picture of it, of the cartoon is shown in the middle here. So we'd have our catalyst with, say, a pore and an active site in it. The polyolefin would come in and absorb into the pore and then be positioned for a cleavage at the star, at the active site, and it would start spitting out the small molecule cleavage product, and the catalyst would eat its way through the chain, pumping out the small molecule, and then when the polymer, that chain is eaten up, now the catalyst is empty, and another new polymer from the bulk would absorb. So this is the opposite of a chain growth polymerization, in that we have long chains, we would have small molecule products, and basically nothing in between. And I should say that this idea of precessivity is not limited to chain cleavage, to depolymerization reactions. So the olefin polymerization is a chain growth process. DNA repair is a chain growth, is a precessive process. So in DNA repair, for example, the enzyme is absorbed onto DNA chains and moves up and down the chain looking for errors. It fixes the error, then moves on to find the next error. So the concept of precessivity is really the absorption of the substrate onto the catalyst, and the catalyst does multiple steps of on that substrate without releasing it. So that's a general phenomenon. Okay, so we envision that this might be able to be accomplished with inorganic catalysts and pores. And another colleague of mine, Wenyu Huang, pointed out that he had made these materials that are shown here. So this is a solid silica core, where Wenyu and his group have deposited platinum nanoparticles on that core, and then they grow mesoporous silica as a shell over top the material. So kind of in cartoon form, it's here. So you see the solid core, the little orange balls should be the active platinum sites, and then you have mesoporous silica. And the question was, would this kind of catalyst work in that precessive fashion in a hydrogenolysis process? And what would the implications of that be? So the good news is, at least for our study, that it appears to work in a precessive fashion. So in this top plot, these are the size exclusion chromatography curves of the starting polymer. That's the black one. Then we do hydrogenolysis of the polymer and convert about 30% of the mass into things that aren't starting material. And that's this orange curve. And then we extract away those soluble species, and what remains behind is the green curve. And what you see is the molecular weight doesn't change. So over this conversion, what we're doing is we're eating up some select portion of these, but the molecular weights of the chains don't change. We convert some and leave the rest behind basically unreacted. And what's converted is made into this low molecular weight distribution, which we extract and analyze by GC. And you can see this rather narrow Gaussian distribution. So this has all of the properties that we attribute to a precessive kind of deconstruction. The bulk polymers consumed without change to the molecular weight, that's shown by the SEC. The reaction mixture contains high polymer, low molecular weight species, and very little in between. And then the products are relatively narrow distribution, and that doesn't change over the course of the conversion. So at low conversion of polymer, maybe 5%, we get this kind of distribution, all the way up to some 80 or 90% conversion. So that can be contrasted with platinum on silica, where we've just left the core bare. So we didn't grow the mesoporous silica over top the catalyst. And you see, when you do the cleavage reaction, this is the starting polymer, and necessarily you get the non-precessive intermediates from random cleavage. And then the small molecule products are really this tail. So when we extract we get this broad distribution out, and that's really the tail of the average cleavage from random CC bonds being broken as they're absorbing down onto this platinum on silica catalyst. And this is kind of the general phenomenon that most catalysts give when you look at, say, hydrogenolysis of polyolefins. But I would say more generally, the random cleavage of polymer chains are going to give these distributions. So that doesn't allow for selectivity. So this is really powerful, and it's really powerful because it means we can design the sites, the platinum sites, to give certain behavior, and then we can affect the architecture to control how the processivity occurs, how the polymer exposes itself to the active sites for cleavage. So a second version of this kind of catalyst puts pores in the center. The shape changed because the core changed, but the idea was in the previous catalyst we have dead end pores, and so the polymer goes in and then the product has to come out through the same pores. And the idea here was, well, the polymer could come in, get cleaved, and then find its way out through other pores through the center core. And that has a remarkable effect of allowing us to get to longer chains in a really rather Gaussian, quite nice distribution. It decreases the gas formation because we don't have very much tailing into the low molecular weight. And it gives really quite high activity for conversion. So that's shown here. So the catalyst I'm describing and that we have as a cartoon here is shown here. The stars correspond to the CC cleavage. So we're measuring the number of carbon-carbon bonds that are broken as we're doing the conversion. And then the bars represent how much of the polymer itself is consumed. So you can see that at, I think all the time, this is normalized by time. So this particular catalyst, this mesoporous core catalyst, is very effective at deconstructing the polymer to these this Gaussian distribution. It's not the fastest. So these are the speeds for CC cleavage at a fixed time. And you can see ruthenium on carbon is faster. It breaks CC bonds at a faster rate per time than this catalyst. And this was the original core shell catalyst here. It's even slower. But you can see how much better this is at converting polymer because we break the chains into longer, rather specific lengths. So more of the cleavages go selectively to making the products we want, whereas a catalyst like ruthenium on carbon makes a lot of methane, which we don't want, and that's reflected in the high activity for cleavage, but the low activity for polymer conversion. And I think overall, this is a really powerful principle for thinking about how you're going to get selectivity and how you're going to get to relatively specific products that we can design. So we tried to understand a little bit about why we were getting longer chains. And the way we did that was through molecular dynamics simulation models. So this was done by Eric Lauten's group at Northwestern. So what they showed was that when you have a system with an active catalyst site in the center of a pore, like we do in this porous core system, then the polymers chains tend to stretch out more. Whereas in the closed pore, the polymer chain kind of condenses on itself. So that leads to the much better selectivity and the much higher activity associated with the porous core catalyst. And that I would say matches with our matches with our observations at least. The other thing we learned from this study is that in this system, so as I said, we had a closed end, and the product has to diffuse out through the pore that's covered with polymer already. And that can keep it close to do additional cleavage, what we call overhydrogenalysis. So the idea behind this porous core, and what's illustrated nicely in Eric Lauten's simulation is that when you do a cleavage here, now the product can move away, and the chance of it coming back and undergoing a secondary cleavage to give lower molecular weight species, and those are the things that lead to gases that we don't want to make. So the way around that is to have this open pore system. But you don't have to do that. You can just understand the idea that if you need to get the small molecule away from the catalyst, we can just physically remove them. So the way we've executed that is to build what we call a semi-batch reactor. So the studies I've told you about up until this point would be a sealed batch reactor where you have the catalyst, the polymer, the products, they're all contained within the same reactor, and it's sealed and heated for some period of time. So what we've done in this semi-batch reactor is we allow the hydrogen to flow in, and then anything that has sufficient volatility, just a little vapor pressure, can get transported out of the reaction mixture and end up and get collected now in this condenser. And so that has a pretty significant effect on how the reaction's performed. So we're doing this now at very low pressure, just 1 atmosphere of hydrogen, and we can compare the conversion and the selectivity. So at 1 atmosphere of pressure, the catalyst in the sealed reaction makes really a lot of gases. We're about, at this conversion, about 50% of the mass is going to gases, because the small molecules are trapped in the reaction mixture and can get back and get recleaved. In contrast, in the semi-batch system where we allow the volatile species to escape, we get a much less gas at the same conversion, and we're instituting this so-called reactive separation that gives us the products directly. So you no longer actually even have to extract them out. They come into the form whatever they're made at by the catalyst. So this also gives us some opportunity to do some controls. So without hydrogen, without catalyst, you see that the conversion basically doesn't happen, and nothing ends up being transferred to the condenser. And only if you have a little bit of silica do you get anything, and these ends up being kind of broad kind of hydrocracking kinds of products. So that strongly indicates that the catalyst, there's a synergy between the catalyst and this reactive separation for increasing the reaction and the selectivity of the conversion. So I don't know how I'm doing on time. I think that's probably about right. So with that, I will just finish. All of this work was funded our work in iCoop was funded by the DOE in the Office of Science as part of this EFRC iCoop. And so these are our partners. And these projects I think are pretty nice because we get contributions from researchers all over the country to influence how we're thinking about the reaction. So you heard about ideas generated at Illinois, at Argonne, at Northwestern, and in Ames Lab. So with that, I'll also, I guess, as part of this discussion, take any questions.
Okay,
Thank
thank you
you.
very much, Aaron. Appreciate all of our speakers today for taking time to talk to us about projects in plastics recycling. So we have a couple of questions in the chat already. So if you do have a question, you can still type it, and we'll try to get to everything. Let's see here. Somebody asked, and I think any of you could answer this, to briefly describe the hydrocracking process, and what post-processing is needed to reuse that polyethylene after hydrocracking.
I can take the first stab at it. I think Aaron showed a nice few graphics about generally he was talking about hydrogenalysis, but the batch reactor design is what we use for hydrocracking. It is a matter of just throwing all of your species into the reactor. For hydrocracking, we pressurize it with hydrogen up to in the range of like 30 to 50 bar. So these are really high pressure. And then the separations are really like we have a gas collection bag, and then the liquids and solids can be separated through some centrifuging as well as some dissolving of some different solvents. And then generally the solids that we get out are cleaned, like we can separate the catalyst from them through the same like solvent selection filtering procedure. So they can then be used in any sort of like extrusion, melt processing, solvent processing method to produce, a usable plastic.
I don't know if anybody wants to add anything to that, but if I may, I'm going to ask a specific question to both Alex and Aaron as well. Do you guys think about the cost of hydrogen or the efficiency of using that hydrogen, because hydrogen is not a cheap reagent? And especially I was, thinking about this when Aaron, you mentioned your 1 atmosphere pressure hydrogen. So just wondering if you could both comment on that.
Yeah, I can make a quick comment. We've done a little, so we're not funded for techno-economic analysis in any way, but people have done kind of assessment on that. So hydrogen is an expense. And so I commented on making gases and methane that raises the amount of hydrogen. But let's say you're making C20, you actually don't need very much hydrogen. And most of the TEAs suggest that hydrogen is not really the most significant cost. The catalyst is a pretty significant cost in a lot of the real systems. Sorry, real systems is a funny thing for me to say, because obviously our catalysts are not commercial and not likely to become commercial in their form. I mean, the synthesis is going to be not scalable in the way that industry tends to like. So I should say that ours are to understand how processes work, not to deliver a final product. That being said, so I think we get hung up on hydrogen as a community because of biomass, where you have to get the oxygen out, and there is a very significant hydrogen cost there. But in particularly in polyolefins, I think it's as long as you're efficient with your hydrogen, I think it's not going to be a problem.
Louise, anything to add to that? Just from your industrial perspective.
Yeah, well, we have the same view of Aaron, in the sense that it will be necessary, not a large amount, and you have to consider that probably these catalytic solutions will have to be applied close to an industrial site. So you already have sources of hydrogen depending on the process you have. So there is a potential synergy on that as well.
Awesome. I'll jump in there. And Eric, I actually had the same question too. And I saw the hydrogen. I was like, ooh. So I'll ask this question from the chat. In the manufacturing process of biodegradable plastic, how could we improve the thermal stability of used polymers or their degradability in water? So this may be an Alex question.
So that's a really good question. I can tackle a little bit from the water aspect. When it comes to polyolefins, that's traditionally what our center's been focusing on. It's nearly impossible to do anything with water and polyolefins. We do have some works that look at certain enzymes that can break down plastics or oxygenate parts of polyolefins that can make them slightly more water soluble, or at least in some less aggressive organic solvents. But there is an aspect of like throughput for these, for enzyme degradation, biological methods. They're just a little bit slower, even though they can be very selective. It's a difficult thing to chat with polyolefins, at least. But stuff like Aaron mentioned, like PET, PEOs and stuff, they have a lot more viability in terms of like biodegradation and using easier organic solvents, water as well. So
Awesome. Aaron, anything to add to that?
Yeah, I think biodegradable polyethylene is going to be a dream for a while. Unfortunately, I don't know. So my personal feeling is that Kamala should stop calling me. Is that like there's a place for biodegradable polymers, but it might not be a solution overall. And I sort of fear that if we were producing biodegradable polymers on the scale that we made polyolefins, then they would just end up in the atmosphere as CO2. So people have asked me, what's the case, what's the case for doing any of this? Isn't it better just to sequester the carbon in a landfill? Polyethylene will last for, I don't know, somewhere between 200 and 1,000 years. At least the time release for CO2 is less. And that's true. So that's that, if you think in that picture, maybe you don't want biodegradable materials, but we also have a problem. Even in the US, we have a problem with landfills, and we actually are running out of space in our landfills. So people are worried about this. Nobody wants a landfill in their backyard. So building a new landfill is really a challenge. So I don't know how we're going to solve all this, but on the big scale, I don't think biodegradable is necessarily the best solution for the scale of polyolefins. I sort of hope that we figure out ways to recycle them, because then, I sort of hope that we'll not need to pump so much petroleum, and we won't, we'll have a sustainable source of a material that we would use over and over. And I think that would, if we can do that efficiently, that could reduce our CO2 footprint, our manufacturing footprint, but also still have the benefits that we have from using polyolefins as they exist. I think we're pretty far from that, as witnessed by Louise's talk. I mean, right now, to implement anything like this, we're going to be pyrolyzing, and that makes sense because that's the technology we have at hand.
All right, Luis, anything else to add on this topic?
Yeah, I agree that exactly the advantage we have on polyolefins to be as strong as in make it difficult to make it biodegradable, right? So it's very stable and make it very difficult. So we don't really see a way on this direction. What we have close to that would be, as I mentioned, solvent-based technologies, that we are not necessarily breaking the molecule, but you're dissolving the polymer. So it has two advantages. One, it's not thermo intensive, right? And it's segregated, right? Because if you are solubilizing PP, you have PP on the end, right? And so the effort now on this is very related to achieve levels of purity where you can achieve food grade flexible material. If we can do that with the solution, we would have a good solution for segregation. It probably won't be as broad solution because you have to have a particular polymer to do that, but it can be a part of the toolbox of solutions for circular.
Okay, ask another question. So this is a little bit of a longer one, but bear with me. So the size of polymer chains are a significant challenge for recycling, as everybody has noted. Additionally, Aaron was discussing the use of porous materials for the catalyst, and Alex mentioned that the time it takes for the catalyst to break down different molecular weights is an issue. And so all of these things, make me think about the transport of polymers. So is this an issue that needs to be considered on top of the catalyst chemistry? I could see the design of larger scale reactors to implement these catalysts and ensure the appropriate mixing and transport for efficient degradation.
Well, so let me quickly talk about transport within our catalyst system. So we have paid a lot of attention to trying to determine if there are mass transport effects in these systems. And so the way we've gone about that is looked at the different chain lengths from small molecule to large molecule and looked at rates of CC cleavage. And we've done other things like we've changed the activity of the catalyst but left the pores the same. And all of these kinds of experiments and also kinetic models suggest that we're not mass transport limited in the pores for the polymers. However, so this solid catalyst core versus porous catalyst core taught us that we are mass transport limited for getting the products away from the catalytic sites. And that was an important lesson for us to learn. So the polymer was holding stuff in place and we were getting more and more cleavage than we wanted. So that matters. Baron Peters in our center has looked at mass transport of particles within melts using theoretical models, and their study is basically that in the melt there is not a mass transport problem of polymers and catalytic materials on nanoparticle scale. So I think they're talking about up to half a micron or something as you're mixing well. You have to mix well though, so that's important. And you have to be in conditions where you have enough hydrogen around. So at least for hydrogenolysis, that matters as well. So we cannot ignore mass, and actually heat transport might be a bigger problem. So you have to be really careful that so these things are in melts, and say we're at somewhere between 200 and 300 C. And if you're not very careful about reproducing your conditions, temperatures can vary wildly, and mixing will generate gradients in these reactors. So you have to mix really well. And there was a really nice paper from Javier Ramirez. Anyway, sorry, I'm missing a part of his name. Alex, do you know? Javier, he's the editor of Green Chemistry. Now I sound like even a bigger idiot. Okay, anyway, so they studied mixing in these reactors of polymers. Yeah, so you do need to be really careful with how you're mixing and that you have sufficient mixing. And they have some nice models for that. That was like a nature
chemical engineering or something.
Yeah.
I'm familiar. Yeah.
Earlier this year. So that's a very nice study that points out things you have to worry about in these systems.
Yeah, I'll just quickly add from our viewpoint is the batch reactors we have only have magnetic stir bars in order to stir these polymer melts, which they don't. The stir bar doesn't actually mix a polymer melt. And it's because of this really high viscosity that you need these like ultra high torque impellers that are just difficult to fit on like lab scale reactors that we have. So in our experiments, we see the mass transport limitation, and that's just because we don't have good mixing in the system. So it is, like Aaron said, it's a matter of how well you can actually mix these systems. And in extremely high molecular weight polyolefins, these are viscosities that are in the thousands to millions of Pascal seconds and stuff that just require, I mean, that's another aspect too of process design of how much power do you need to supply in order to just stir the reactor. And there's going to be the balance between how long you want the reactor or how long the reaction is going to take place, whether or not you stir it, and whether or not, like, hey, is 10 hours unstirred better than 2 hours stirred just because you needed X amount of power in order to do so.
Perez Ramirez. Sorry, I had to look it up.
Thanks. Louise, I'm curious your opinion on this, the transport in catalysis.
Yeah, at this moment, what we are facing is that we have certain catalysts that we are working with, certain processes, and we have to start thinking about the scale up. So it's more about how we are going to design the reactors, right? What kind of reactors you have to design, and you have all these issues related to the viscosity of the polymer and others, and you can see in the literature that you have different configurations. Some people trying FCC style reactors, for example, for this kind of, because sometimes you need some level of regeneration of the catalyst. So the FCC could be, but not a usual FCC. You might need stages on that as well. So and another point that Alex mentioned also is how you feed the waste, the melted waste to the reactor. And we have done, as we have a lot of knowledge on extrusion, we have also studied extruders as a way to do the initial feed and mixing for the and you have to on the I would say industrial scale, you have to think about all kinds of contaminants, right? Because dealing with the real waste, you have from, I don't know, dirt to other kind of things. So it's also one optimization problem, where you're going to remove each of these contaminants, where makes it more sense, and also that Alex and Aaron mentioned, the problem of the catalyst deactivation. I believe this could be a bigger problem on this kind of solution, because you have almost the periodic table as contaminants on these materials. It comes from a landfill, for example. Well, how can you have a catalyst robust enough to deal with that? And how much you will expand, on the other hand, to remove these contaminants to protect your catalyst. So we still have major issues to be solved to achieve a good solution.
Okay, so another question from the audience. Do you have any advice on where to start learning about polymers and the process of potentially converting a polymer to a new polymer material?
Jeff Coates wrote a nice review about this in Nature Materials a few years ago. Let me see if I can find the link. Can I post? Maybe I can type.
I think you can as a participant, Aaron. I think you can post. And if you can't, if you send it to us, we can send it out. Thank you for that. Review articles are always helpful.
Yeah, let me see. Yeah, I think I mean, he's not the only one, but that one's the one on, I think of as polymer to polymer conversion. But there's a few groups working on this, and their reviews on this. Sorry, I'll find it. Maybe Louise or Alex wants to chime in.
I can just quickly add, in the context of like polyolefins, there's a lot of work now on trying to upcycle them into dynamic covalent networks through series of either reactive extrusions or CH functionalization. So I believe Frank Leidfarth has a recent review article on CH functionalization of polyolefins so that you can kind of convert them into high value or high performance materials as well. So I think I can also post a similar one. I believe Aaron just posted as well. So
Awesome. Well, I'm looking at my tech support and I see that we're coming up upon the 3 o'clock hour, and we do have a stop point there for this webinar. So I think instead of trying to squeeze in one final question, I will just thank our panelists and ask if you have one final thought you'd like to offer up on the way out.
Recycle first.
Facts.
And don't buy new stuff. I mean, in the end, you know, at least what we talked about is, or what I talked about is, years out from having an impact, I guess, probably. But you know, every time you buy something new or replace something, you're generating waste. There's plastic associated with it, but other things as well. And sustainability is, you know, in some ways on us. Which makes a lot of people angry to think about that because it's hard to control, but there are things we can control ourselves.
Excellent point.
And I would add that look for circular and more sustainable solutions on day-to-day consuming, right? So there are a lot of companies doing stuff, interesting stuff. So interesting products to be, so awareness about this is very important. And also, I think it's a good moment to be a chemist or a chemical engineer. We have the opportunity to solve this, right? Someone created this in the past, but now it's up to us to solve it.
Okay. Alex, final word?
I think Aaron and Luis both have great takeaway messages from that. But yeah, I think it's a matter of just being cognizant of also what sort of plastics you're using. Anytime you can try to choose a plastic that's like a single material, move away from single use plastics and multi-layers and stuff like that is always a benefit just because they're difficult to recycle and handle separately. So just, you know, pay attention to those resin codes and stuff you may see on your materials. So.
Excellent. Well, thank you all for your wonderful presentations today and this helpful discussion. I'd like to thank all of the participants who tuned into this workshop today. Stay tuned. We have other workshops coming up later this month. So, you know, look out for some more stuff from us as we continue to have dialogue about sustainability. Oh, I think Peter's going to show the upcoming workshops. Good job. So we have our next workshop is going to be on November 22nd. And then our final workshop of this semester will be on December 6th. And so you can also scan the QR code and put those on your calendar. Share with your friends. Eric, anything else to add before I close this out?
No, I think that was perfect, Malika. I'd like to thank Malika as well for helping put on this webinar and IGS for their support for this series.
Excellent. And thanks again, everybody. Have a lovely weekend and a long one if you got it.
Yes, absolutely.
Thank you.